Hello everybody and welcome to today's video. Today we'll be finishing off chapter 3 of Calculus and Vectors. Chapter 3.6 revolves around optimization problems, which are a combination of all the topics we've learned so far implemented into word problems. So the two main types of problems we'll be discussing would be where we maximize something, for example maximizing area, and where we're minimizing something, for example minimizing costs. So we're going to take a look at two problems revolving around each topic. So first, before we dwell deeper into solving any particular problem, we need to outline a general approach. So when solving optimization problems, we need to follow these steps. So first, you need to know what you're looking for, right? So you need to identify the question, what the question is asking. Then you need to define your variables. It's very important for you to outline what you're using as your dimensions, for example, if you're using length and width, or if you're using x and y. As long as you say let x be width, you should be fine. Then you should also draw a diagram, because usually those diagrams are what are going to help you solve the problems. It's very difficult to solve optimization problems without actually building some kind of diagram, because it's very hard to visualize what is going on. Next, you need to identify the quantity that needs to be optimized within the question and write an equation for it. So if you're dealing with area, you need to know all the different types of area equations you might need. If you're optimizing a rectangular field, you know it's going to be length times width. If you're optimizing a rectangular field that was divided into 5 equal sections, right, that are all, for example, rectangles, you know that each rectangle would be length times width, but then at the end you'd have to multiply by 5, right? So you find the total length and width, or sorry, the total area of the surface you're working with. After you've done that, you need to identify the independent variable. You need to, for example, say you're gonna focus on only length. We know that the width in the question is, for example, like 2 times less than the length. So you could express the width as the length divided by 2. So that is what you need to do for every single question. After you identify and write everything in terms of your independent variable, you could write a function in terms of the independent variable. So using the example of a rectangle with length times width, where the width is twice as little, we know that we could write the expression length times width, or in our case it would be length times length divided by 2. This is the type of function you need to do. Then you should state any restrictions that might occur on the independent variable. If you're talking about area again, you can't have, for example, one of the dimensions being 0. It also can't be so that the numbers are negative, because we can't have a negative area or a negative side length. Once you're done that, you need to differentiate the function. The reason for that is what we're going to get into in the next portion, but essentially, since we've already learned that you could find the maximum and minimum values using this first or second derivative test, you could figure out your x values using that test. So if you want to maximize an area, you would use the appropriate local maximum or local minimum for that problem. Then you'll need to determine and classify the critical points. And lastly, you'll need to just answer the question posed in the problem. It is also important to always keep the context of the problem in mind, because usually it will dictate an interval or the domain of the question. For example, you can't go over the cost of $500. That means your x value, which is your cost, for example, can't be over 500. It also can't be 0 because you're not getting anything for free. Lastly, you'll need to verify your answers, since you have to know that the answers you give make sense in any given context of the question. So if everything here makes sense to you, let's get on to solving some of the questions. So the first one we're going to deal with is maximizing area. As I said, you're only going to deal with like 2 different topics or 2 different types of optimization problems. They could be varying in different approaches, right? You might not be maximizing area, you might be maximizing production, for example, but they all have the same type of steps that go into solving that question. So here we're given the following question. A farmer wants to enclose and subdivide a rectangular field into 5 congruent plots of land. He has 6,000 meters of fencing. If the area to be enclosed is to be a maximum, determine the dimensions of one of the plots of land. So what we know is that we have 5 congruent plots of land, we know the fencing, and we know it needs to be the maximum area. So first, let's draw a diagram because this usually helps us visualize. So this is kind of what's going on. Over here, I said that each long side, so this side right here, could be y, and the shorter sides, so these, could be x. Then we could create a equation. So the first equation would of course be the total fencing that we have. We have 10 long sides and we have 6 short sides. And so we get 10y plus 6x is equals to 6,000 meters, where x and y must be greater than 0. If they're less than 0 or are 0, we don't get an area, we just have a straight line. To maximize the area of the plot, of each plot, we need to know its maximum area in the first place, right? So the area of this entire thing will be x, the short side, times y, which is 1 plot, and we have 5 of them, so 5x times y. I'm gonna say that m is equals to 5x times y, where m is our maximum area. Now we could use these 2 equations to solve for x. So what we want to do first is to express everything in terms of one variable, right? So that is the first step that we had here. Define the independent variable. The independent variable for us is x. To rewrite y as a dependent variable, we could rearrange this equation here. So 10y is equals to 6,000 minus 6x, so we just brought this to the other side. Now we could isolate 6, so we just pull it out from both of the like terms, and we're left with 6 times 1,000 minus x. Then we could also divide by 10 on each side to isolate for y, and so we get this right here. Now we see that we have a 6 and a 10. They both have a common factor of 2, so we could factor out the 2, and now we get 3 times 1,000 minus x divided by 5. Now we know what y is in terms of x, and now we could substitute it into our equation for m. So once we do that, we get m is equals to 5x times 3 times 1,000 minus x divided by 5. Opening the brackets and expanding, we get m is equals to 3,000x minus 3x squared. So now we could do either the first or second derivative test to find and classify the critical points. So first, let's find the first derivative, so we could do the first derivative test. So we have m as our variable, so of course we get dm over dx, and that is 3,000 minus 6x. Again, you should know your derivative rules by now, but in case you don't, here we'll just drop the x. Here, the 2 becomes a 1, and then 2 times 3 is 6, so we get negative 6x. We also know that for us to have a local maximum or a local minimum, we must have the derivative to equal to 0. Right? So we say it's equaling to 0, so we get 3,000 minus 6x is equals to 0. There are no points where this value would not exist because we have a polynomial function. So now we get this equation here. We could divide this by 3 and we get 1,000 minus 2x is equals to 0, so x is equals to 500. We found an x value, but we do not know whether or not it's a local maximum or a local minimum. So let's classify it as we did before. So to classify it, we could either use, again, the second derivative test, or we could create an interval chart to check if our function is increasing and then decreasing, or decreasing and then increasing. So in our case, we only have one critical point, 500, so our intervals would be from 0 to 500, and from 500 to infinity. This is our function, and if the number is between 0 and 500, we get a positive value, which means m is increasing. Then, if we go beyond 500, the value is negative, so m is decreasing. Since we're going up and then down, that means we have a maximum point. So now that we know that x is a max and we need to maximize the area, that means we did the right thing. So now let's solve for y. Here we just substitute 500 in for x and we get y is equals to 300. So the dimensions of one of those plots is 300 meters by 500 meters. If we go back to our diagram here, we could see that it's not exactly to scale because we said y would be our our longer side, but it clearly turned out shorter. But nonetheless, it helped us understand how to approach this problem. If you don't get your diagrams exactly to scale, that's completely fine. You don't know the answer yet, so you can't say that x should be longer than y or y should be longer than x. That would be determined in the future. So hopefully this approach makes sense to you, because now we're gonna talk about minimizing costs. To minimize costs, it's nearly the same thing, but now we need to find a local minimum for our x value. So this problem is talking about minimizing costs, and here it is. The owners of a small island want to bring electricity to the mainland. The island is 95 meters from a straight shoreline at the closest point. So here's our little diagram. From the straight point, we have 95 meters. Then the nearest electrical connection is 220 meters along the shoreline from that point. So this entire line is 220 meters long. It costs us $24 per meter to install the cable across the water, and it costs us $10 per meter to put electricity across the land. So we need to find the least expensive way to install the cable. Nobody wants to spend more money on something that they don't have to. So of course we want to optimize it so we get the least cost. So here we drew out the diagram. All we know so far from our question is this 95 meter and this 220. However, since it says that it's cheaper to route it on land, we want to maximize so we have as much of it on land as possible, right? And then the least of it as possible on the island. However, we need to still keep a proportion. We can't go all the way over here, right? 220 and 95 up, because as you might know already, the hypotenuse would be shorter than the sum of these two numbers. So this is the proposed plan we've created. First of all, let's define this as x. The reason we're defining this as x is so that we could express the length of the wire that's going across the water in terms of x as well. If we were to do it the other way around, so we put 220 minus x here, this would be 220 minus x squared, which would make a much more complex equation. The reason for why we're saying x is because, first of all, it's an easier variable, and second of all, 220 minus x is the length of how long the wire would run on land. And again, that is something we need to know to form our calculation. The only thing that we don't know now is this expression here. But as you could see, we have a 95 meter long straight connection here. This is a land that is perpendicular to the 95 meters, as stated here, is straight from the short line. So this right here is a right angle triangle. And if it's a right angle triangle, we could use the Pythagorean theorem to form this expression. So you get the square root of x squared plus 95 squared is equals to this side. Now we need to figure out the total cost it would take for us to run the wire inland and on the shore, right? So putting together everything we know, we could express it as the following function. So c of x is equals to 10 times 220 minus x. So $10 on land times how long the land is, plus the cost of running the wire over water times how long the cable is over water. We know that x cannot be 0 because then that would mean we are running all the way over here, which is again not something we can do because you will not be optimizing anything. And we know it must be less than 220 because then if it was bigger, you would just go across the given restrictions in the question. So now, using that, we need to expand what c of x is equals to. Nobody likes to work with square roots, so we're going to rewrite it as the power of 0.5. Now we know how to deal with powers, so taking the derivative of this question, it's not that complicated. So first we open the brackets, right, and we got 2,200. That becomes 0 when we take the derivative of it, which is why we don't see it anymore here. The derivative of negative 10x is simply negative 10. The derivative of this expression is a little bit more complicated because you have to apply your chain rule. So what we have to do first is take the derivative of the outside, right? So we have 0.5, so we carry it over here, so we get 24 times 0.5. Then we have to subtract 1 from the power, and so we get negative 0.5. Now we need to multiply this entire expression by the derivative of what is inside the brackets, which would be 2x, because this is a constant and this is x squared. Now we just need to simplify. If we do simplify everything correctly, we should get negative 10 plus 24x divided by x squared plus 9,025 to the power of 0.5. Again, you could make this a square root, but first of all, making a square root is a little bit complicated on this application. And second of all, again, nobody likes to work with square roots. Powers are so much better in terms of derivatives. Now we need to find the values where the derivative is equals to 0 or where it does not exist. Unfortunately for us, this is a rational function. So of course there is a value for which c prime of x does not exist. But first, let's deal where it equals to 0. Now, to find where it equals to 0, we just equate the two, right? So we get this equation. We could bring the negative 10 to the other side, and now we get this. We see that we have 24x here divided by something. So we could actually just multiply, so cross multiply this, and we get the expression here. Oh, sorry about that. Now we have a 0.5 on this side, so that's the same as a square root. How do we get rid of a square root? We square it. We have the same things on both sides, right? So nothing's stopping us from squaring both sides. You must remember, when you're squaring everything, you really need to square everything. So this 10 is no longer 10, it is now 100. This loses its 0.5 because it became 1, and this, instead of 24x squared, it became 576x squared. Now this is a simple polynomial equation, so we just expand, simplify. We have 100x squared and 576x squared, so let's bring the 100x squared on this side, and we get this. Plop this into your calculator, and you should get x is equals to 43.5. We cannot use x is equals to negative 43.5 because it doesn't fit into our restrictions for x. The only other thing we have to check is where c prime of x does not exist. But if we look carefully at our denominator, we see that it's x squared plus 9,025. No matter what we do to the x value, this will never be negative. Because if you remember, this is a parabola that opens up and it starts above the x-axis. So it'll never reach 0. So now we found a single x value and we need to classify whether or not it's a maximum or minimum. So now again here I use an interval chart to check for what this value is. In our case, we see that it is decreasing and then increasing. Again, to check it, just plot this value into your equation and see whether or not it is negative or positive. If it's negative, it's decreasing. If it's positive, it's increasing. If we are decreasing and then increasing, that means that we have a minimum. So it is a minimizing question, and we found the local minimum, which means we are on the right track. Now we just need to solve for the appropriate distances. So if you remember, when we were talking about this question, we said this value is x because it made this computation easier. However, since we're trying to actually find the costs, right, we need to find this length right here. So this right here would be the value of 220 minus x, which is 156.5 meters. So the rest is quite simple. We know that the cable should be run from the point of 156.5 meters across the shore, so around probably like somewhere here, and then the rest of it should be run up like this. It doesn't ask us how much the least expensive way costs, so there's no point of us calculating c of x, but if it did, you just need to plop in your x values here and you'd figure out the cost. So now we're done with chapter 3.6. There are more complex questions in terms of just like how you need to think about them in the textbook, so I heavily recommend you trying out questions 9, 15, 23, and 25. If anyone has any questions, please just leave a comment. I'll try to answer you as quickly as I can. Again, I'd like to thank you all for watching, and I hope to see you guys next time. Bye bye!